This is a lesson on Bernoulli's principle. In prior lessons, we've seen how fluids responded to forces, and in static situations, it's always easier to use a force model because everything sums up to zero. When you have fluids in motion, or anything in motion, it's more useful to use a state function, and energy is the easiest and most straightforward to apply. So Bernoulli's principle for me is the application of conservation of energy with fluids. Let's look at what I mean. The application of conservation of mechanical energy in a fluid will look like this. And if you're familiar with this equation, on this side I always put the first energy state, right? This is the initial energy state, E initial. And on the other side I put the final energy state, E final. Well, when I look at a fluid, I don't really think in terms of energy. I think in terms of pressures and in velocities. We also have some sort of potential energy stored or amount of fluid above a certain point. And all of these terms can be represented in this way. Some sort of pressure on one side, some sort of kinetic energy going on, and some sort of height. In a final energy state, we can think of some other pressure, some other final kinetic energy, and some other potential energy. Pressure at a depth seems to be an easy application of this. P1 plus some sort of rho GH has to equal P2. Energy allows us to incorporate velocity and height differences. Let's look at an example of how to fly a plane. An airplane has an effective wing surface of 16 meters squared. Okay, so surface area, I'm going to note that. Area is 16 meters squared. That is generating a lift force. In level flight, okay, so it's level flight, so it's not moving upward and it's not moving downward. So it's level flight. The airspeed over the top wing is 62 meters per second, and the airspeed beneath the wings is 54 meters per second. Because there's a velocity difference between these two surfaces, there will be a force difference, a pressure difference, and a force difference causing a lift. And so I've drawn an airplane wing here. You'll have to forgive me for how simplistic it is, but this is the airplane wing. And when I think about the Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. So I'm thinking about two different places, two different states, and what we're going to look at here is air moving on the bottom of the wing as opposed to the top of the wing. So I'll put top over on this side, and I'm going to put bottom over on this side. Okay. In my simplistic drawing, I've noticed that there's an area on the top and the area at the bottom, and those are both the same. It's going to be the same. It could be different in different situations, but we're going to assume it's the same. There's a pressure difference. There's a pressure on the top and there's a pressure on the bottom, and we don't know what those are. We have no clue, and we don't care what those values are. We don't know what those values are, so we're not going to worry about what the values are, and you'll understand in a second why. As I'm explaining this, I'm thinking about the plane flying level through the sky. So the velocity overall for the plane is in this direction, and so it's not moving up or down, and I'm thinking about the forces on the plane. Well, there's a force on top here of the wing because of pressure. The pressure on top has to be related to the force on top over the area on top. And there's a force on the bottom, which results in a pressure on the bottom. Overall, the force on the bottom will be larger than the force on top, causing an overall lift force. When I look at these two forces together, they're going to add together to be a lift force. And so when I look at the free body diagram of the plane, there's going to be a lift force on the plane, and there is the weight on the plane. And in order for it to go straight through the sky, these two will be equal to one another. And so when it says, what is the weight of the plane? I want to find what is that lift force. I'm going to write out what I know about the lift force. The lift force equals the force on the bottom minus the force on the top. According to pressure, remember pressure equals force over area. If I solve that equation for force, I would get pressure times area. So I would get the pressure on the bottom times the area on the bottom minus the pressure on top times the area on the top. We said those two areas were equal to one another. And so I'm going to say the pressure on the bottom minus the pressure on the top times the area will equal that lift force, which will equal the weight of the plane. So if I find the difference in those two pressures, then I can find this weight force. And so you can see why I'm not concerned about the values. What I'm just going to do is solve for a term, this whole thing together. I'm not solving for each one of these values separately. I'm going to solve for this term. Well, when I look at this equation, I can solve for it. This would be P top, and this would be P bottom. And so what I'm going to solve for is P bottom minus P top for this equation. What I'm going to note is that it's level, and we're going to assume that the height difference here is negligible, such that this height, h1 and h2, are equal to one another. h1 equals h2, and I can cancel that term out on both sides. So my equation is simplifying. If I solve for PB minus PT, the pressure on the bottom minus the pressure on top, well, I'm going to bring that over here. We'll bring this over here. I get 1/2 rho V1 squared minus 1/2 rho V2 squared. I can simplify this one step further. V1 squared minus V2 squared. And now I can plug in some numbers. 1/2 rho of error is 1.29 kilograms per meter cubed. That was included in the problem. And I'm going to put these velocities in. V1 is the velocity on the top, and V2 is the velocity on the bottom. So the velocity on the top is 62. I'll put that in, 62 squared. The velocity on the bottom is 54 squared. If I had these reversed, I would get a negative number, and that would be alarming to me because I expect this to be a positive number. The force on the bottom is larger than the force on the top. The pressure on the bottom is larger than the pressure on the top. We get an overall motion upwards, or a lift force upwards. So this should be a positive value. When I run this through the calculator, PB minus PT, remember, I don't know what these values are. All I care about the difference that I can plug in here. When I run this through the calculator, I get 598.56 pascals, which isn't very big at all. That makes sense. I'm not a big difference in the air from the top of a wing to the bottom of the wing. So, but it's enough pressure to cause a lift to overcome the weight. I converted this to ATMs just to compare it to how many atmospheres this is, and it is small, 0.0059 atmospheres. So about 0.6% of the atmosphere, which isn't very large. So let's solve for this lift force. The lift force equals this difference times the area. So I'm going to take 598.56 pascals. I'm going to multiply by the area, which I wrote down here, 16 meters squared. And I will get force out of this. The lift force on this plane equals 9,576.96 newtons, which seems reasonable. Seems maybe like a small plane. It has 16 meters squared, which doesn't seem very large for a plane. If I calculate a mass, if I let all of this be mass, it's 977.24 kilograms. So about 1,000 kilogram plane. Doesn't seem very, very big.